Morning, everyone. Welcome back to the new session and the new topic, which is the digital design. So, as of now, we have understand how the different code works and uh, how we can come up with a different codes like error detection code, correction codes, and some binary codes as well. Okay, so this is what we have studied in the previous class. Now, suppose I have to design any logic. Okay, so in that case, the basic logic gates is really very important to understand how what is the function of those logic gates and what is inside of those logic gates. So because without knowing how this particular logic circuit works or logic gate works, you will not be able to design design any of the circuits. So in this particular lecture, we will be discussing about the basic logic circuits or the basic gates or the different kind of gates, especially like we will talk about some basic gates, some universal gates, some uh, special gates as well, and we'll see what is the difference between all these things. Okay, so why we are discussing this logic gates? Because if I have to design any of the logic function, suppose I have to add two numbers, so it is not just like I can do it easily. We to make a adder circuit, we must use some of the logic circuits. Okay, and that logic circuit is made of the logic gates. Okay, and the logic gates are made of transistor, diode, and the Mosfet and other kind of devices. Okay, so you should know how this particular logic gate works and what is inside that logic gates and what are the different conditions, different property of all the logic gates. Okay, so to understand these things, basically the logic gates are divided into three categories. The first category is the basic gates, which is uh, NOT gate, OR gate, and the AND gate. Uh, if we talk about the second category of the gate, that we call it the universal gate, where the NAND gate and the NOR gate are considered under the universal gate. Why we are calling them the universal gate, I will tell you in detail later on. Okay, and the third kind of gate is like exclusive gate, which is the XOR gate and the XNOR gate. Okay, so why we have differentiated these gates in three different categories and what is the advantages of all these gates, we'll check it out. And what is the reason behind saying this logic gate is the universal gate, this is the exclusive gates, we'll check it out, all these things. Okay, so let us start one by one. First, let us discuss with the basic gate, because some of the things you are already aware of how this kind of logic gate works. So I will quickly explain the things because you know the things. So we don't need to spend too much time on that, and uh, we'll see it. Okay. Now let us start from the NOT gate or the inverter gate. What is the NOT gate and how it works? Basically, we have already studied. Suppose if I want to make the complement of any logic, whatever the logic I have, like if the input is at logic 1 and I want to make it complement, like because in the digital system we have a two logic level, logic 0 and the logic 1. Okay, and if I have to make the complement, first one's complement or any other things I have to do, in that case NOT gate is important. So NOT gate, what is the function of NOT gate? NOT gate or the inverter, basically whatever the logic we have, if the input is at logic 1, then the output will be logic 0 and the vice versa. And this kind of logic we call it the NOT gate or the inverter gate. Okay, the basic schematic of this one is like, yes, if I have an input A, the output of this A is the complement of this one. A bar indicates the complement. So output X is nothing but this will be a complement of input A. Okay, if we try to understand in that case how it will look like, suppose if I'm providing the input 0, in that case output will be 1, and if input is equal to 1, in that case output will be 0. So this will be the truth table for the NOT gate or the inverter gate. Now the question is, suppose I have to design any inverter or any NOT gate, so how it looks like, how we can design this kind of circuits. Okay, so to design any of the circuit, let us recall the first lecture or the briefing lecture we just which we took a few days back. Let us try to recall that thing. We had a transistor based logic, and which was looking like this one. Okay, having the structure something like this. So this was some of the structure. Yeah, we had some base resistance. Here we had some VDD. Here we had some, let us assume RL. Here we had RB. And here I provided, let us assume input A. And at the point here, I took the output X. Okay, so this was the basic structure which we have studied, okay, before. And I just told you, if the log A is 0, in that case this transistor will be in the on state, and if this is in the on state, this X will be directly connected to the ground, so we will consider X is 0. Okay, and if A is equal to 0, this transistor will be in the cutoff region, and the X will be nothing, this will be the voltage VDD minus the voltage drop across this resistance RL. So if we try to make the equivalent circuit of all both the cases, so let us try to see how the equivalent circuit looks like. So if A is equal to 0, okay, if A is equal to 0, then how the circuit will look like? If A is equal to 0, in this case, this transistor will act as an open circuit. And if this transistor will act as an open circuit, the equivalent circuit will look like this one. Okay, we have some open switch and that will be grounded, and here we are observing X. Here I have a VDD, here I have a RL. Okay, let us assume the voltage across this RL is the VRL. So whatever the X I will receive, the X will be VDD minus the voltage across this RL, means the VRL. Okay, so this is what we have already studied before. Okay, similarly, if X is equal to 1, in that case, how the circuit will look like? Sorry, if A is equal to 1, then how the circuit will look like? Because we have provided A is equal to 1, so this transistor will be in the on state. So the equivalent circuit will be something like this one. Okay, and here we will observe the X. Okay, so whatever the switch we have, that will be closed, and this is the RL. Here we have the VTD. Okay, so now what I will get, because this is short circuited, so the resistance between X and the ground is less than the resistance between VDD and X. So this like the lower part will start dominating, because the current flow between the X and the ground will be more as compared to the VDD and X. Okay, so because see here, there is a less resistance, so the X will be grounded, but definitely this RL will try to pull up. If the strength of this RL is very less, if the RL is very small, in that case the pull up, like upper side, will start dominating. So we need to keep RL somewhat higher so that it cannot start dominating. So this is how the equivalent circuit looks like, and both the logics works. But in reality, this is what we have already studied. Okay, but in reality, suppose I have to design any circuit based on the CMOS based. Okay, what is the CMOS based? CMOS means the complementary metal oxide semiconductor based logic. Okay, you may have heard about the CMOS logic, CMOS structure. Okay, what does it mean? It means that if you are designing any of the circuit with the help of MOSFET, then those kind of logics are called the CMOS based logic. It means that CMOS means that if any of the circuit is consist of the PMOS as well as the NMOS kind of transistors, like NMOSFET or the PMOS transistors both, then those kind of circuits are known as the CMOS kind of logics. Okay, now let us see, if I have to design an inverter, so how we can design an inverter based on that CMOS logic, because this is very important to understand how actually logic looks like. Okay, so before I explain you about how the circuit is designed based on the MOSFET, I need to explain how the MOSFET works, or the basic fundamental of MOSFET. Okay, so you may have, I'm assuming that you may have studied the MOSFET and MOSFET characteristics. Okay, so you know the fundamental of MOSFET and other things. Okay, so let us try to see. Basically, there are two types of MOSFET. One is the P MOSFET, and the second one is the N MOSFET. Okay, now if and the symbolical representation of PMOS and NMOS is something like that. Let me write it. Let me draw it. Okay, so the Okay. Uh, so this is the symbol for N MOSFET. Okay, this is the simple symbol or the simplest symbol of the NMOS transistor. And similarly, the symbol of PMOS transistor is something like this. Okay, we have to put some bubble on it because these both are the complementary to each other, and we have to provide some terminal gate and some source terminal, some drain terminal. And there is one more terminal like body terminal, and the body terminal is always connected to the if you talk about it is connected to the in the PMOS transistor. It is like in both the primary side, it is connected to the source terminal, right? So body is connected to the source. So I'm not considering the body for the simplicity. So this is how the PMOS and NMOS transistors look like. Basically, this N MOSFET and the P MOSFET are nothing but they are working as a switch. Okay, so and this N MOSFET and P MOSFET can be turned on with the help of what is the voltage at gate. G is nothing but this is the gate voltage. Here we have a drain voltage. D means drain voltage, and S means the source voltage. So we have here we have a three terminal: gate, drain, and source. There is one more terminal which is the body terminal, which is connected to the source one. So I'm just not using that one. So let us quickly understand how these logics are working actually. If you closely see, I have provided the drain of the NMOS transistor towards to the higher side, and the and the source of the PMOS transistor towards the higher side. What does it mean? It means that the direction of current flow is in the opposite direction, like drain to source and the source to drain. Like the current flow in the NMOS transistor is from drain to source, and the current flow in the PMOS transistor is from source to drain. So that is why we have to give like drain terminal at the higher side and the source terminal at the higher side in a PMOS transistor. So this is the first reason. Second thing is, I just told you this gate terminal, whatever we are providing, this is nothing but this is the controlling terminal. This controlling terminal decides whether this MOSFET will act as an open circuited or it will act as a closed circuited. So to understand these things, because I'm not going into more detail, you can go through some lectures which is available on my channel, so you can go through it. So what happens? I just told you, because this gate terminal act as a controlling terminal. So how it works? How it will decide whether the NMOS transistor is on or off. So if G is equal to 0, okay, if I'm talking about the NMOS transistor, and if G is equal to 0, this transistor is in the off state. Okay, so this is what fundamental you should understand. Later on I will tell you. Similarly, the second case could be if gate terminal is equal to 1. In that case, this NMOS transistor will be in the on state. So if it is in on state, means the open circuited, and if it is in the off state, on state, then it is the closed circuited. Similarly, if we talk about the PMOS transistor, in that case, if the gate is equal to 0, then the PMOS transistor is opposite than the NMOS transistor, and it will act as a on, like it will be, the switch will be on. And if the gate terminal is 1 means the logic 1, right? So I'm talking about the logic ones. So if gate is equal to 1, in this case the PMOS transistor is in the off state. So this is what you should understand how it is working actually. So I'm not going into more detail. Few things that you have to understand. First thing, how we can control this NMOS and PMOS transistor with the help of gate. So I just told you, if G is equal to 0, then the NMOS will be off and the PMOS will be on, and the vice versa. Second thing, the current flow in the NMOS transistor is from drain to source, whereas the current flow in the PMOS transistor is from source to drain to source, and in the PMOS it will be the source to drain. Now let us talk about if I have to make some inverter kind of configuration based on these circuits, whatever PMOS and NMOS transistors I have, then how we can make it. Okay, so let us try to make. I just told you the PMOS transistor will be in the off state if the G is equal to 1 and vice versa. So let me try to make some circuit. Okay, and then you will be able to understand. Yeah, I'm just quickly making it, but the detailed fundamental you can understand from the lecture, from the channel. Okay, so here I have a, let us assume A, and here I have a X. Okay, now what I have done, I have just like see, this circuit is nothing but this is just like what we made for based on the transistor and resistance. Okay, so the I have replaced this RL with the Pmos transistor and the transistor with the Nmos transistor. Okay, this is what I have done. Okay, now let us try to see whether this logic is working or not. Okay, so suppose if A is equal to 0. Okay, if A is equal to 0, then how circuit will look like? See here, if A is equal to 0, what it means, the gate terminal of this PMOS, this is nothing but this is the PMOS. Okay, and this is the NMOS transistor. If A is equal to 0, so the gate terminal of PMOS transistor is at logic 0. And if it is at logic 0, we know that the PMOS transistor is in the on state. Okay, and if it is in the on state, means the resistance will be very small. Okay, so there will be some on resistance R on due to the PMOS transistor. Now let us talk about the NMOS transistor, because if A is equal to 0, so the gate terminal of NMOS is also 0, and we know that if gate is equal to 0, it will act as an off state. Off state means there will be an open circuited between the X and the ground. So this is how the X will look like. Now if you see here, what was the VDD that we can observe at X, because there is no path between X and the ground. Okay, so there is a path between VDD and the ground, VDD and the X. So what it means, that VDD will be transferred to the X, means the output X is nothing but this is high. Okay, so I have provided A is equal to 0 and I am getting X is equal to high logic. Similarly, if we talk about the second case, okay, if A is equal to 1, in that case what will happen? Let us try to see. If A is equal to 1, in this case, this is 1, this is 1. We know that if A is equal to 1, NMOS transistor will be in the on state and the PMOS transistor will be in the off state. Okay, so NMOS is in the on state and the PMOS is in off state. So the equivalent circuit will be like, there will be an open circuit between the VDD and the X, and there will be some on resistance between the X and the ground, which is, this is the on resistance of NMOS transistor. So now if you see here, this X is now connected with the grounded. So X is nothing but this is low. So we see here A is equal to 0, so X is equal to high, and A is equal to 1, then X is equal to low. What it means, this circuit is acting as an inverter that is made of the CMOS based logic. Why I'm calling it the CMOS based logic? Because here I have used the PMOS as well as NMOS transistors. So in any of the circuits, if both kind of transistors are available like PMOS and NMOS, in that case we can call them the CMOS. If in any of the circuit only PMOS kind of logic is work, then we can call them the PMOS logic, PMOS based logic. If only NMOS kind of transistors are there, then we can call them the NMOS based logic. But if both are present, then we can call them the complementary metal oxide semiconductor logic or the CMOS logic, because the NMOS and the PMOS transistors are complementary to each other. Okay, so these two are the complementary to each other. That is why we call it the CMOS based inverter. So this circuit is nothing but, this circuit is the CMOS based inverter. Okay, so this is what this is how the inverter can be made based on the MOSFETs. Okay, so in case if you have any doubt, you can ask the questions on this. Otherwise we can move ahead. Any doubt anywhere? Anywhere, if you have any doubt, you can ask the question. So this was the first kind of logic gate that we call it the NOT gate or the inverter gate. Okay. Now, yeah, so why I'm just explaining this much of detail, because you should know, suppose if I have to make the inverter, so how it looks from inside, this is also very important, right? So it's not like uh, just you have to understand the block diagram of this inverter. You should also understand how it looks like from inside. Okay, so this is important. Now, the second kind of logic gate is the OR gate. Okay, second kind of logic gate is the OR gate. OR gate means what? Okay, suppose the symbol of OR gate looks like this one, where A and B are the two logical inputs. A and B are logical input, and X is the logical output. And the output is given with the help of A plus B. Okay, that we are calling it the ending of all these things. Suppose, so if I have two inputs A and B, in that case, the total possibilities could be like A and B both could be 0. A could be 0, B could be 1. This could be 1, this could be 0, and 1, 1. So we have total 4 possibilities. Okay. So based on all those four possibilities, let us try to see how the output looks like. Okay. So let us try to see here. Suppose I have A and B both are input, and I can have a 4 possibilities. X is equal to A plus B is there. So A plus B is there means what? If I'm adding 0 plus 0, so I will get output as logic 0. Here I am doing the logical addition, okay, not the arithmetical addition. That carry will be generated. Here there is no carry, only the logical addition will be there. Okay. So then if I will add 0 plus 1, then I will get 1. 1 plus 0, I will get 1. And 1 plus 1, that, see, if I am doing the arithmetical addition, in that case 1 plus 1 that gives 0, and 1 is carry forwarded. Okay, carry is there. But if I'm talking about the logical addition, what it means, this indicates a logic high, and logic high that gives you the logic high if you are talking about the ORing. Okay, so the A plus A that will give you the 1. So this is not like the logical or the arithmetical addition. So this is what the truth table of this OR gate is. Now the question is how this kind of the OR gate can be made with the help of diode or transistor. So let me quickly make a logic circuit based on the diodes. Okay, what is the property of diode? Because you have already studied the diode. Okay, what is the property of this diode? Diode property is, if the this potential is high, so in that case this will act as a this will pass the current, and this will act as a on state, like this will be the resistance is very small. Okay, but if I have a diode and the logic 0 is here and logic 1 is here, in that case this will be in the off state, or the resistance is very high. We know that forward bias and the reverse bias kind of concept. Okay, so let us try to make the circuit for OR gate based on the diode, and you will be able to understand how it can be designed. Okay, so suppose I have one diode is here. Second, I have a 2 inputs, so I need to consider 2 diodes. Okay, this is not necessary that you can make it with the help of diode only. You can also make you can make with the help of transistors. You can make with the help of Mosfets. So this is possible. You can do it with any of the way. Okay, so let us try to see here. If some RL is here, and here I am taking the output X, and here I have a 2 inputs. Let us assume A and B. Okay, so let us assume this is diode D1 and this is diode D2. Okay, now let us try to see whether this logic or this circuit is acting as a OR gate or not. Okay, so let us take consider the first case, 0 and 0. Okay, if 0 and 0 is there, okay, 0 and 0 is there, like A and B we are providing logic 0, so these both the diodes will be in the reverse bias. Okay, both the diodes will be in reverse bias, so this will be open circuited. So directly X will be connected to the RL, so we will get some ground voltage with some resistance RL. Okay, so the ground will be transferred, so logic 0 will be transferred. Now let us talk about the second case. If A is equal to 0 and the B is equal to 1, in that case, because A is equal to 0, so this D1 is in the off state, but because I have provided B is equal to 1, so this diode D2 will be in the on state. Okay, and if it is in the on state, because I have provided logic 1 here, so this logic 1 will be transferred to X. Okay, because this is the on state and the resistance between B and X is less than the RL. So this logic 1 will be transferred to the X. So X will be 1 if B is equal to 1. Similar case, so here we will get the output X is equal to 1. Third case could be like if A is equal to 1 and the B is equal to 0. So diode D1 will be in the on state and D2 will be in the off state. So the A will be transferred to the X. And if both A and B is equal to 1, 1, so both the diode D1 and D2 is in the on state. So logic high will be transferred to the S. So this is how we can say the equivalent circuit of this OR gate based on the diode logic looks like. Okay. Do you have any doubt on this logic, on this circuit? Anyone? Okay. If you have any doubt, you can ask the question. So this is how this works. Okay, so this is the basic. Yeah, similarly you can make it with the help of a transistor. Similarly you can make it with the help of CMOS. Later on I will tell you how we can make with the help of CMOS logic, right? So I will tell you later on details in more detail later on. Now let us try to understand. Suppose if we have designed some of the an OR gate. So what are the property of this OR gate? If we try to see here, see here, if any of the input, like this is really very important, try to understand here. If any of the input is kept as logic 0, see here, what I have done, I just connected A to the ground. If any one of the input is kept at logic 0, so whatever the input I am providing to the second input, like A, B is equal to 0 and B is equal to 1, I am getting the same kind of logic at the output. What it means? It means that if, yeah, let me make the logic circuit. So suppose I have a OR gate, something like this, and I have a 2 inputs, and one of the input is grounded. Okay, and the second input is, let us assume I'm providing the some square wave pulse. Okay, this is what I'm providing. So what will be the output? Can you tell me what will be the output? How the output will look like?
So square wave.
Square wave. Okay, it will follow the same kind of pattern, right? See, because I have connected one of the input to the ground, so whatever the input I will provide to the second input, that will be followed at the output. So the output waveform will be same as the input waveform. So this is how the waveform will look like. What it means? It means that this circuit will act as a buffer logic. Okay, this circuit is nothing but this is the buffer. Okay. Buffer means whatever the input I have provided, if it is following at the output, so we can call them the buffer circuit. Okay, so this is how the OR gate can be considered as a buffer gate if I am connecting one of the input to the ground and the second input is connected to any of the input, then the output will be same as the input. Okay, and here this signal or this ground will be act as a enable signal. Okay, so the second input will act as a enable signal. So this is the enable low. Like if I'm providing logic low, then this buffer will be enabled. Let me repeat it again what I'm saying. If I have to use this OR gate as a buffer, in that case I need to enable this buffer gate by providing logic low to one of the input. What it means, this kind of buffer is the active low kind of buffer. Active low means if I'm providing logic low to the enable signal, then this will act as a buffer circuit. Okay, so this is how this circuit works. Now let us talk about the second case. Okay, what is the second case? Suppose I have a OR gate. Okay, and now see here, if we check the second case, if I'm providing logic 1 to any of the input, okay, if I'm providing logic 1 or I'm fixing logic 1 to any of the input, whatever the input I will provide, it does not matter, I will always get the logic high. Whether the input is 0 or 1, it does not matter, right? So suppose if I have connected one of the input with the VDD, so if there is a change in the input, okay, I will always get the logic high. Output will always be the VDD, okay, not the grounded. So there is no change in the output. This will be maintained. So output I will get always logic 1 or VDD. Okay, so this is what we can call it the inhibit signal. So we are inhibiting the logic to high. Okay, so this kind of the circuit we can call it inhibit signal. Inhibit signal means like if after providing any of the input to any logic, if it does not matter whatever the input I am giving and the output is same, like it is not changing with the change in the input, then we can call them the inhibit signals. Okay, so this is how the OR gate works, and this is important to understand. Do you have any doubt, anyone?
What is meant by that one or VDD? I mean, there should be always one only, na?
Yes. So we are always getting one. So see, if I want to inhibit the logic, what it means, just connect one input to the VDD, and even though if there is some change in the input, it does not matter. The output will be same or output will always be high. Okay, so that is why we are calling it the inhibiting the signal. Okay, so the output will be always maintained. Yeah, so that I will discuss in more detail when I will talk about the NAND gate or sorry, AND gate. So you will be able to understand, might be this inhibit signal can be different for the different logic gates. Okay, why I'm just explaining this kind of thing, because see, sometimes I want to get the same kind of output whatever the input is. In that case, I need to connect one of the terminal to the grounded, and that will act as a buffer. Sometimes I want the same logic always, like logic high always, not changing with the inputs. So in that case, I need to inhibit this one. Okay, but if I want to make any logic which is inhibited to logic 0, so we need to use a different kind of logic gates. What are those logic gates? I will tell you. So let me finish this AND gate, then you will be able to understand how we can do that. Okay, so this is how the structure looks like. Okay. Any other doubts? Fine. So this is the important thing that we should consider. Now let us talk about the AND gate, how the AND gate looks like, and how we can make it. AND gate is basically, the symbol of AND gate is like if I have a two input A and B, and the logical multiplication is given here, like output is nothing but the logical multiplication of both the input whatever I have. So in that case, if I have a in four combination for A and B, like 0 0 0 1 1 0 and 1 1, so the output will look like 0 cross 0, 0 into 0, that will give you the 0. 0 multiplied with 1, that will give you the logic 0. 1 cross 0 or 1 multiplied with 0, that will give you the 0, and 1 into 1, that will give you the 1. So output will be high only if all the inputs are high. Okay, so this is important. In the NAND gate case, the output will be high only if all the inputs are at logic high. Okay, otherwise the output will be low. Okay, so this is how this looks like. Now let us try to make it try to make this circuit based on the diode. Okay, so how we can make it, let us try to see. Yeah, just for this I will make, otherwise for others I will not make this thing. So So suppose I have this kind of a structure having D1 and D2. Now let us try to see whether this circuit is acting as a AND gate or not. How this will work. If A and B both is equal to 0, okay, if A and B both is equal to 0, in that case, what I will get? I will get like this is 0, this is 0. Yeah, this will be in the forward bias. This will also be in the forward bias. So this logic 0 will be connected to this X. So X will be 0. If any one of the A or B is low, then this will provide the direct path between the ground and the output. Okay, so the output will always be high. In case if A and B both are 1, so this will be the off state, this will be the off state. Now the X will be VDD minus V into RL. So for the last case, which is 1, 1, in that case, I will get X is equal to VDD minus VRL. For other case, we will get logic low because both the diodes are in the reverse bias. So this is how the equivalent circuit we can make based on the diode and resistance logic. So this is what we call it, the diode resistance logic. Okay. If we try to make some of the logics based on that, let us try to see how we can make it. Suppose I have an AND gate. Okay. I have a 2 inputs. And let us try to see clearly here. If I am providing any one of the input to logic 0, so the whatever the input I will change, it does not matter. It always gives you the logic 0. Okay. If I have connected any one of the input to grounded, so even though there is some change in the second input, it does not affect. The output is always 0. What it means, if I have connected like this, and if there is some change in the input, something like this, output will always be 0 or grounded. And if it is like that, we can call it, this circuit is inhabited to logic 0. Okay. So this is the inhabited to logic 0. Similarly, let us try to see the second case. The second case could be, suppose I have a AND gate, and if somehow I have provided the VDD to any of the input, let us assume I have provided the logic 1 to any one of the input. So whatever the input I have, that will be passed to the output as it is. So we can also call them, I can make the buffer circuit with the help of AND gate as well. So whatever the input change is there, I will get the same kind of output. So what it means, this is the buffer circuit. Okay, so this circuit is nothing but this is the buffer circuit, and this VDD will act as a enable circuit. Okay, so VDD will enable to make this logic as a buffer. Okay, so this is how we can discuss the AND gate.